When work is done against a conservative force, like gravitational force, it gets stored as potential energy. Let's consider a body lifted vertically to a height h from the surface of the Earth. Some work needs to be done against the gravitational force of the Earth to lift the body, which is stored as potential energy in the body. When the body is released from height h, the body gains kinetic energy and loses an equal amount of potential energy. The law of conservation of energy holds good in this case, as the total energy of the system is constant. Like gravitational force, the electrostatic force between two charges at rest, expressed by Coulomb's law, is also a conservative force. The gravitational force between masses m1 and m2, separated by a distance d, is expressed as g into m1 m2 by d square, where g is the universal gravitational constant, which is equal to 6.67 into 10 raised to the power minus 11 Newton meter square per kilogram square. We can see that the gravitational force F is inversely proportional to the square of the distance d between the masses. Similarly, the Coulomb or the electrostatic force F between charges Q1 and Q2, separated by a distance d, is expressed as K into Q1 Q2 by d square, where K is a constant which is equal to 1 by 4 pi epsilon naught. We can see that the electrostatic force F is inversely proportional to the square of the distance d between the charges. When a force acting between two bodies is inversely proportional to the square of the distance between them, that force is said to be obeying the inverse square law. We observe that both gravitational force and electrostatic force obey the inverse square law. We know that work done against gravitational force is stored as gravitational potential energy for the mass in the gravitational field. Similarly, work done against electrostatic force is stored as electrostatic potential energy in a charged particle in an electric field. Let us now discuss the electrostatic potential energy of a charged particle in an electric field. Consider the electric field of a positive charge Q placed at the origin O. Let Q0 be a positive test charge located at point S. To bring the charge Q0 from point S to a point P closer to charge Q, some work has to be done against the force due to the electrostatic field Fe. The external force F required to move Q0 should be just about sufficient to overcome the electrostatic repulsive force Fe on Q0. Therefore, we can say that the magnitude of the external force F is equal to the magnitude of Fe. Let this be equation 1. The external force F should not give the charge Q0 any acceleration. The net force on Q0 must be 0. The charge Q0 must be brought from point S to point P at a very low constant speed. The work done to move Q0 from point S to point P is denoted by WSP and is stored as electrostatic potential energy for charge Q0. If we remove the external force F, then the charge Q0 moves away from Q in the direction of the electric field and gains kinetic energy such that the gain in kinetic energy is equal to the loss in its electrostatic potential energy. The sum of the kinetic and electrostatic potential energies of charge Q0 is always a constant or conserved. We know that the work done by the external force F to move charge Q0 from point S to P is denoted by WSP. This is equal to the integral of external force F dot dr in the limits S to P, where dr is the distance between the 2 points. Let this be equation 2. From equation 1, we know that the magnitude of the external force F is equal to the magnitude of force Fe due to the electric field. But the direction of the electrostatic force of Fe is opposite to that of the external force F. Therefore, we can say that external force F is equal to minus Fe. Let this be equation 3. Substituting the value of the external force F from equation 3 in equation 2, we get WSP is equal to minus integral Fe dot dr in the limits S to P. Let this be equation 4. In equation 4, the work done against the electrostatic force is stored as electrostatic potential energy. Hence, at every point in the electric field, the charge Q0 possesses electrostatic potential energy. Let the potential energy of the charge Q0 at points P and S be UP and US respectively. The work done by the external force F, as given by equation 4, is also equal to the difference in the electrostatic potential energies of the charge Q0 at the points P and S in the electric field. Let this be equation 5. The work done by the external force F is WSP is equal to delta U. Let this be equation 6. From equations 5 and 6, the work done by the external force WSP can be rewritten as delta U is equal to UP minus US. Let this be equation 7. The difference in electrostatic potential energy between 2 points in the electric field of any arbitrary charge distribution will be equal to the work done to move a charge from one point to another. The work done according to equation 7 is independent of the path followed to move Q0 from S to P without accelerating Q0, and is dependent only on the initial and final positions. Hence, the electrostatic force Fe is a conservative force, and the work done against the electrostatic force Fe is independent of the path followed. Adding a constant C to the electrostatic potential energy at points S and P will not alter the values of the difference in electrostatic potential energy between the charges and the work done WSP. Hence, we can choose a convenient reference point where the value of the potential energy is 0. Let point S be at an infinite distance from the charge Q. The electrostatic potential energy of Q0 at point S is US equal to U infinity is 0. Therefore, the work done according to equation 7 can be rewritten as WSP is equal to UP minus U infinity, which can be written as WSP is equal to UP since electrostatic potential energy at infinity is equal to 0. That is, U infinity is equal to 0. Let this be equation 8. Based on equation 8, the electrostatic potential energy of a charge Q0 can be defined as the work done by an external force to bring a charge Q0 from infinity to a point in the electric field of any charge distribution is equal to the electrostatic potential energy of the charge Q0 at that point.